Well, welcome to everyone. Good morning, good afternoon, or good evening, depending where you are. It's actually 5:30 a.m. for me, so if the sun comes up behind me and actually blinds the camera, I will move around. As Kamal said, this session is really about global risk and resilience of infrastructure. In the past, there have been other global assessments of physical assets, of buildings and the built environment, but infrastructure actually presents us with a different set of challenges, because to actually assess the global risk to infrastructure, we not only need to look at the physical assets, at power stations, roads, telecommunications towers, and so on and so forth. We actually need to see how damage or loss of those assets would then actually affect the operation of infrastructure networks. So we need to move, in a sense, from a focus not just on assets, well, the assets continue to be important, but also onto the flows and the networks and the essential services which those assets provide. And I think this is a core challenge, because people don't actually depend on infrastructure per se for their lives and livelihoods. They actually depend on the essential services which infrastructure provides. So as part of the upcoming global flagship report, which Kamal just mentioned, the idea is to do an update of what we already know about global risk, but really focusing in on some of the major infrastructure sectors. For example, power and energy, telecommunications, transport, and so on and so forth. But also then in a number of countries, hopefully not a few countries, quite a few countries, we're actually then going to drill down and really look at the resilience of infrastructure networks. So this session is going to just give a bit of an overview of some of the challenges we're going to be faced in assessing risk and resilience in global infrastructure. So we have an excellent group of speakers today. Let me just introduce some of them. We have from Infraestructura in Colombia, Dr. Omar Dario Cardona and Dr. Gabriel Bernal. From the Cima Foundation in Italy, we have Dr. Roberto Rudari. From Geohazards International, we have Dr. Janice Rogers, who's the Chief Operating Officer. From the National Disaster Management Authority of the Maldives, we have its Deputy Chief Executive, Mr. Omar Fikri. From Santa Lucia in the Caribbean, we have Mr. Howard Wells, who's Director of the National Integrated Planning and Program Unit. And very much last but not least, from the University of Oxford, we have Professor Jim Hall, who's a Professor of Disaster and Climate Risk. So with no further ado, so we can get on promptly with this session, I'm going to ask the colleagues from Infraestructura, Gabriel Bernal and Omar Dario Cardona, to make a presentation on multi-hazard risk modeling for disaster risk and resilience assessment. So Gabriel, take us away, please.
Thank you, Andrew. Yeah, so hello to everyone who is attending. Thank you, Andrew, for the introduction. And the purpose of this presentation is to provide you an overview of what we're going to be dealing with, as Andrew said, for the multi-hazard probabilistic risk assessment of infrastructure at the global level. So next, please. As you can see, assessing risk to infrastructure is quite a challenge, and even more doing it at the global level. So if we want to provide any kind of useful and sensitive information about risk to the infrastructure, to the global infrastructure, we need to come up with some methodology, with some approach that is robust and sound enough so that we can say something meaningful about all the different sectors that compose the infrastructure portfolios of the countries in the world. Next. In this line, next please, thank you. Um, I'm sorry, my screen. Andrew, can you hear me?
Have you got an internet problem at your end, Gabriel? Can you hear us? He's frozen.
Hi, Andrew, can you hear me?
I can hear you now, so please continue.
Okay. Thank you. Yes. So I was saying that we start with some system model that has some specific domain and is composed by a network of interdependent assets. Through these assets, some service is rendered or some commodity is flowing, and all these elements are susceptible to damage once an hazard event occurs. So once the event occurs, we're going to be facing some direct loss due to the physical damage to the assets, but also some loss related to the unbalanced demand and offer conditions that are changing with respect to what was previously established before the event occurred. Now, this is a very complex problem that needs to be addressed gradually. Next, please. So basically, what we would have to do is to focus first on the physical damage, on the physical loss that is derived to the assets once the events occur. Next. So once we know the system and we are familiar with it and how it is confirmed, we need to evaluate the performance of the system to external disturbances, which are basically natural hazards. We're talking about earthquakes, tsunami, landslides, droughts, floods, tropical cyclones, among others. Next. And all these hazards need to be modeled using state-of-the-art physical models with an event-based approach. And this is key because we need to be able to quantify events, to simulate events of hazards, so that after we simulate one event, we can quantify the extent of damage to the system and to its components, and quantify all that as a direct physical loss. Next. So we need to define, and we need to imagine all the possible ways in which hazard is going to be manifesting in the territory. This means multiple events of multiple hazards. This means thousands of possibilities that need to be simulated, because each event will imply a different disturbance to the system. Next. So moving from hazard to direct consequences implies applying physical probabilistic risk assessment. Next, please. At the end, what we get is a collection of events. Each event comes from a natural hazard event, but it's now expressed in terms of physical loss and some probability of occurrence. Of course, low disturbance events have higher probability of occurrence. Very high disturbance events have lower probability of occurrence, or in other words, they are less frequent. But at the end, we get a very high, very extensive collection of events that is making up for a fully probabilistic multi-hazard risk assessment. Now, in practical terms, it is quite unpractical to work with the full set, the full collection of these events. So we seek to condense everything into metrics. Next, please. So we're talking about risk curves. For example, the PML curve, which is a very used risk metric that relates return period to loss amounts, or point estimates, like, for example, the average annual loss, which basically is telling us all the, it's kind of condensing the whole risk process into a single number. And there are others that will be defined and will be complying with international standards and will be delivering all the information we need to assess risk at country level. Next, please. So in the short term, with this huge effort, what we hope to get is some physical risk metrics at country level. Maybe you can go to the next, please. You should be seeing a map. Thank you. So at each country, we hope to express, no, go back, please, to my screen froze, so I'm not following. Yeah, that's great. Thank you. What we're seeing here is what we hope to achieve in the short term. Some metrics, some expression of risk at the global level for each country that is telling us all the information we need in terms of disaster risk to the infrastructure portfolio of each country. So this means point estimates, this means curves and risk profiles at the national level, as is illustrated here. Next, please. But we won't stop there, because we need to consider the effect that climate change is going to be implying to some of the hazards, particularly to hydrometeorological hazards. So for these hazards, we need to simulate the effect of climate change and to see how climate change is going to be modifying meteorological variables at the local level. We're going to be using the emission trajectories defined by IPCC, which are the representative concentration pathways that are more or less a very constrained and bounded way to define different pathways of greenhouse gases emissions. And these will have some effect at the local level. We downscale that information to some location we're working at, depending on the location of the infrastructure system. And then we can use more than 40 global circulation models with the 4 RCPs, and with several variations to the initial boundary conditions to come up with more than 300 projections of how the local weather will be changing in the future. So this is important because, as you see in the plot, this has 2 main features. It is dependent with time, but also it delineates some intervals at each moment in time. And this is key because the problem is so full of uncertainty, the uncertainty is so deep that the best we can do is to use those intervals, because it's very different to be in the lower bound of that interval than in the upper bound. The implications for weather and the implications for hydrometeorological hazards are completely different. So all these uncertainty is now incorporated into the model, next, so that all risk metrics now are become time dependent and imprecise. Take, for instance, this curve. This is an imprecise risk curve calculated for landslide risk to the highway system of Colombia, using 4 climate change projections up to 2055. And what you can see there is the deviations caused by the many possibilities of the way the future climate will develop around the green curve, which is the current condition without climate change. So we need to look into all these possibilities, all the range of possible variation, because actually the future climate will only be known in the future. So right now we don't know it, and we need to work with imprecise, bounded interval conditions, interval metrics, so that we can express with full transparency what the disaster risk incorporating climate change will be to each infrastructure system. Next, please. So everything, all this I'm talking about will be computed with the CAPRA robot platform, which is a catastrophe risk modeling engine we at Ingenier have been working on for almost 20 years now. Next, please. We have been able to use it globally for many risk assessment projects and initiatives at the global level, at the regional, at the national, and at the local level. So we're very happy to use it now for this infrastructure risk assessment effort. Next, please. So to summarize, if we want to move from risk metrics to resilient infrastructure, first we need a multi-hazard risk profile that gives us information in terms of probabilistic risk metrics that incorporate climate change, that become time dependent and imprecise, and that allow us to define resilience targets, which basically are how much I want to reduce risk sometime in the future. Then we need to define some high resolution infrastructure risk model that incorporates both physical and operational domains of the infrastructure, and that allow us to stratify risk into different layers so that we can differentiate within those layers the possible actions to reduce risk. Next, please. And then we use this model to test all the different possibilities, applications, alternatives that could be developed and implemented for the system that allow us to achieve those resilience targets. Now, as you can see, next, please, this global risk model of the coalition of CDRI will focus only on the first box, which is already a lot, but it would provide the point of departure for this very important and exciting long-run process of achieving resilience. We are totally convinced that the path to disaster resilience starts at a good enough risk model. Next. Thank you for your kind attention.
Okay, thank you very much, Gabriel. That was excellent presentation, I think very, very clear. So I'm now going to pose a question to Dr. Omar Dario Cardona. So I'm just basically going to ask you, Omar, to reflect on Gabriel's presentation. I mean, according to your experience on working on previous global risk modeling efforts, what are the main features a global infrastructure risk model must have? So over to you, Omar. Thank you.
Thank you, Andrew. Well, I think the main purpose of probabilistic risk modeling is to reveal latent disasters, more when most catastrophic events have not yet occurred. To decide, you have to measure, and at a global level, measuring with the same rule allows a ranking or to undertake a useful comparison among the countries that helps them to make risks explicit. A probabilistic and stochastic multi-hazard approach can invite the stakeholders and decision makers to ask themselves what each country can do to achieve a higher degree of resilience and improve their trade-offs between relevance and accuracy. Although a global model for assessing risks in infrastructure cannot include all variables, it can be good enough robust to inform the effect of uncertainty and invite to place the magnifying glass at the national level. Using the same arithmetic, one can take into account the non-stationary hazards, like the climate change related, the interdependence, and the impact on the continuity of floods and services. In summary, it is necessary to use probability to the extent possible. Do not oversimplify. Make decision makers appreciate the complexity and understand what is at stake, taking into account that decisions and actions are what really matters. Thank you, Andrew.
Sorry about everyone. So thanks, Omar Dario, an excellent compliment to Gabriel's presentation. So we're now going to change the focus for the next 10 or 15 minutes and look much more on what's happening in the world of the hydrometeorological hazards affected by climate change. And for this, I'm going to ask Dr. Roberto Rudari from the Cima Foundation in Savona, Italy, to please make us a presentation on hydrometeorological risk modeling, the climate risk and resilience assessment. So over to you, Roberto, please.